Okay, real briefly, this video will cover many of the technical details in determining whether or not you will be able to build a ram pump given your situation. If you don't know what a ram pump is, we'll go into that. We'll go into how to take elevation measurements, how to take volume calculations, how to figure out what the best size ram pump for your situation is, how to correct for elevation. We're going to go into a whole bunch of stuff here, and then we'll go over some of the finer nuances of ram pumps as it relates to practical application regarding plumbing, fittings, types of pipe, filtration, intake, standpipe setup, all that sort of stuff. So this video is basically a technical manual so that you can understand how to design and implement a ram pump on your farm or homestead. I've spent a lot of time playing with ram pumps and learning about them, and I've done a couple different videos, well, many different videos on them, and a couple of them really took off, so there seems to be some interest. So I thought I would do this video because I had a lot of questions along these lines, and I thought I would just make one long video and cover it. All said and done, I think this video is going to be about an hour and a half. I apologize for the length, but I really wanted to be clear and specific on technical details. So I hope you'll bear with me if you're interested in this sort of thing and you want to build a ram pump. I hope this video will help. February 4th, 2020. So I've been promising to get back to this video for quite some time. This video is basically site selection and how you measure and take calculations on a site to determine whether or not you can put a ram pump on a site, and if you can, what size ram pump you can put on, and generally what its output will be, how high it can pump, what the volume will be, all those sort of parameters. So, what is a ram pump? A ram pump is a hydraulically operated pump. Basically, it uses a portion of the water that is falling from a water source to drive the pressure in the pump. Some of that pressure, some of that energy is used and transferred to build pressure in the pressure chamber. The pressure chamber side is the output side that delivers a small portion of the water that is being pumped through the ram pump to your destination. The rest of the water that's going through the pump is wasted. It's not actually wasted, its energy is being used to pump the small portion of water up. So a ram pump will typically pump about 10 times the fall distance. So if you have water falling 10 feet and you have enough water to supply a ram pump, you can basically pump to 100 feet with a portion of that water. And usually that runs somewhere around 10 to 15% of the total volume throughput of the pump. I do have a video on calculating a ram pump's efficiency. Perhaps I'll drop a link below, but you can check that out as well. So basically a ram pump is a hydraulically operated pump, and it uses an air pressure chamber to buffer the hydraulic shock that we're taking advantage of. Hydraulic systems are systems that don't have any gas in them, and so the fluid inside that system is virtually incompressible. Water can be compressed, but it's such a small amount that it's not noticeable. And so instead of letting that shock be a detriment to the system, we take advantage of that hydraulic concept and we use it to pump a small portion of the water going through the pump. So that's basically what a ram pump is and how it works.
Okay, so before we get too much deeper into calculating ram pump stuff, anytime you engineer or design something, you really want to understand the machine that you're trying to design and what's involved in it. You really need to understand the specifics of it before you can really, determine whether it's something you can do. So I'm going to share this link here in this below this video. This is the Clemson EDU link on homemade hydraulic ram pumps. This is by far the best manual that I've found to date, and this is the one that I designed my ram pump from, and this manual has a tremendous amount of excellent information in it. So we should just go into some basic understanding of ram pumps. So I'm going to read this to you, and then we'll go from there. So this information is provided as a service to those who want to try to build their own hydraulic ram pump. The data from our experiences with one of these homemade hydraulic ram pumps is listed in Table 4 near the bottom of this document. The typical cost of fittings for a 1 1/4 inch pump currently is $120 US, regardless of whether galvanized or PVC fittings are used. Now this is an older manual, so the cost is going up a bit due to material costs going up and inflation. This is the basic diagram of how a ram pump works. I suppose we should go over that quickly. Well, we'll come back to that, I think. Let's see, they go into connections a little bit, and using appropriate and proper fittings and connections. Let's see, important pieces. Pressure chamber. A bicycle or scooter tire inner tube is placed inside the pressure chamber, part 15, as an air bladder to prevent waterlogging or airlogging. Inflate the tube until it is spongy when squeezed, and then insert it in the chamber. It should not be inflated very tightly, but have some give to it. Basically, this is going to act as a shock absorber so that the pump doesn't tear itself apart. No information is available concerning pressure chamber sizes for various sizes of ram pumps. Make one for somewhat larger pumps. For instance, try a 6-inch diameter by 24 pressure chamber, or for a 3-inch ram. I will say I have tried many different chamber sizes, and I found that the size of the chamber, once you get to big enough to absorb shock, doesn't matter much, and it will not affect your pump delivery or anything. So don't go crazy on building a chamber. You probably don't need more than 4-inch diameter and 36 to 48 inches tall, unless you're building a massive ram pump like in the 4-inch range or bigger, or maybe even 3-inch. You might get a little bit bigger, but anything below that, from 2 inches on down, you can go down to pretty small. If you're building a 1/2 inch or 3/4 inch or 1-inch ram, you probably don't need much more than, I don't know, maybe a foot tall by 3 inches in diameter. I've tried all sorts of different stuff as shock absorbers. I have not found anything that lasts long term. I have not gone back and retried the bicycle inner tube. I think that is probably your best bet. But what I ended up doing was just, occasionally I drain the pressure chamber out and let fresh air into it, and then fill it back up and run it. And I find that runs for a couple of weeks before it dies down. Ultimately, I want to put a snifter valve in, but that can be a little bit tricky because you have to drill a hole that lets just enough air in without compromising the efficiency of your pump. And I've been a little hesitant to do that since the pump works so well. Let's see. They talk about using they tried to use a 4-inch threaded plug for this pressure chamber so they could get it open and closed. They found that this combination leaked regardless of how tightly it was tightened or how much Teflon tape they used in the seal, which results in, if you have a leak in the pressure chamber water logs out quickly, and then your ram pump doesn't run as efficiently, and it will tear itself apart because now all that shock is being put on every piece of that pipe. One thing with hydraulics, the pressure that you put into a hydraulic system is uniform across the system. So if you have a water shock or water hammer situation in the system, that shock is being distributed to the entire system at the same time. So they say this in turn increased the shock waves and could possibly have shortened pump life. And they say if the bicycle tube should need to be serviced when using the glue cap, the pipe may be cut in half, and then you can re-glue them with a coupling. I don't like doing that. I did find a way around the threaded plug issue. I do recommend you use a threaded plug, except I would get some silicone sealant like you use for aquariums, and I'd put that on the threads of the plug, and I'd thread the plug in, and I'd let that sit 24 hours at room temperature to dry or cure. And then I found that that kept it from leaking, and it made it so that you could open it up later on with a pair of channel locks or a big pipe wrench. You could get that cap back off, but that maintains your seal. So that was how I got around that issue. let's see, so valve number 1 is drive inlet for the water pump. Let's go back and look at this diagram quick here. So this is a on-off valve basically, and this here is a check valve, and this here is a check valve. This check valve is run reverse, so as water flows down the pipe, it pushes the check valve until it slams shut. When this check valve slams shut, that forces through the water shock, that forces this check valve open and lets a portion of the water out and into the pressure chamber. That water fills into the pressure chamber. There's airspace in here, say from like here or so, and that water fills into the pressure chamber because the air allows it to. When the equilibrium between this pressure and this pressure is met, then this valve closes and it holds that pressure in there, and then you're letting that pressure out slowly over time, basically out through your delivery line. And this cycle will keep repeating itself. This valve will fall back due to gravity once there's no pressure holding it, and when it does, it'll open up, water will start to flow again, and it'll come through, it'll slam this valve shut again, that'll push this open again, push another portion of water in, and the cycle continues. So that's how that works. That's basic understanding. Let's see, they get into some pretty in-depth information in here. One thing we do have to cover is drive pipe. So these calculations, these numbers right here, are excellent for calculating drive pipe length. So let's just, oh boy, if I can find a calculator.
Okay, real briefly, I want to touch on the drive pipe of the ram pump. The drive pipe of the ram pump is the water inlet side going to the pump. That usually either comes from your water source directly or comes from your standpipe, depending on the logistics involved in your system and the terrain that you're working in. But basically, the drive pipe is the water flowing into the pump. That drive pipe should not have any air in it, so that you don't have any place for the water to compress except through the valves that are in the pump. And that water in that drive pipe is effectively acting as a sledgehammer. And so just to help you visualize this concept a little more, if you have a 20-foot long pipe full of water that has a certain amount of weight and mass to it, and that's moving in inertia in each cycle of the pump. If you have a 40-foot pipe, that's the equivalent of double the amount of water in there, and it's basically double the sledgehammer that's driving that initial valve in the pump. And so you have more energy available in there. But there are some limitations to that. We'll get into that in another clip. Alright, let's talk about shock wave and refraction wave in a ram pump. So in a ram pump, when the primary, the impetus valve opens, water starts to flow down your drive pipe, and as it flows, it picks up speed, and as it picks up enough speed, it eventually picks up enough speed that it catches that check valve and slams that check valve shut. When that happens, there are actually two waves that happen there. There's a pressure wave that happens immediately when that valve closes. All that moving inertia and water behind that valve is forced to come to a stop. That causes a tremendous pressure spike. That's what opens the secondary valve and lets a portion of the water through. But right after that, there's something called a refraction wave that happens, and that refraction wave is sort of the opposite of the pressure wave, and that travels back up that drive pipe, and that'll either go back to the water source or back to the standpipe, depending on your setup. And if that refraction wave is hindered, you'll end up where your valve won't pop back open. So basically, the ram pump, the water in the drive pipe flows down the drive pipe faster and faster until the impetus valve is forced close. At that point, there's a huge pressure spike that pushes open the secondary valve and lets some portion of the water through. At the same time that's happening, this refraction wave starts its way back up, and so the valve's opened, it pushes the other valve open and lets some water out. We reach equilibrium. The secondary valve comes closed because there's nothing, no resistance now pushing it open, no pressure holding it open. And once that equilibrium is reached, this refraction wave goes back up the pipe. So this is part of why if you have a ram pump with a drive pipe that is too long, you'll end up where the refraction wave will end up meeting the pressure wave and they'll start to cancel each other out. So that's why it's really important that you don't exceed the maximum drive pipe length on a ram pump, or you'll basically just cancel the pump's operation and you won't pump any water. So I just wanted to explain that little detail to hopefully help you visualize a little better. If I can find a decent image or something to help you understand that better, I'll put it up here. Okay.
All right. So your drive pipe length, well, I'll just read this to you so you have a full understanding of it. The length of the drive pipe from the water source to the pump also affects the stroke period. In other words, how long each cycle is. A longer drive pipe provides a longer stroke period. There are maximum and minimum lengths for the drive pipe. The drive pipe is best made from galvanized steel. More rigid pipe is better, but Schedule 40 PVC can be used with good results. The more rigid galvanized pipe will result in higher pumping efficiency and allow higher pumping heights. Rigidity of the drive pipe seems to be more important in this efficiency than the straightness of the drive pipe. I found that to be true also. Drive pipe length and size ratios are apparently based on empirical data. Information from the University of Georgia publications, see the footnote, provides an equation from Calibrate 1958 describing the output and stability of ram pump installations in relation to the ratio of the drive pipe length to the drive pipe diameter. The best range is in length to diameter ratio of between 150 and 1000. Equations to use to determine those lengths are minimum and maximum. Minimum L equals 150 times inlet pipe size, and maximum L equals 1000 times inlet pipe size. So let's look at that. If your inlet pipe is 1.5 inches, say, and we use the 150 number, you have 225 inches. We'll divide that by 12 to get it into feet. So your minimum length would be about 18.75 feet. And then we'll do it again, 1.5 inch times 1,000 be about 1,500 inches over 12 is about 125 feet. And that would be your maximum for a 1.5 inch pipe, or 1.5 inch ram pump. As I mentioned before, mine is about 117 from the water source to the pump. I did not want that entire pump to be pulsing and flexing because it's made of PVC. If it were galvanized, I might be less concerned, and that longer stroke might give me a little bit more efficiency because there's a lot more water's weight and inertia energy in that pipe moving at a given time, slamming against the valve and providing pressure. But it's a really tricky balance between those two, so you're best to stay within these parameters. Let's see, drive pipe length example. Well, yeah, here they did the example. Minimum length should be, yeah, 187 or 15.6 feet. Maximum length the same. They're doing for 1 1/4 would be about 104 feet. And so that's another part of why I did this, because I looked at 1 1/2 inch and I looked at 1 1/4, knowing I might need to bump back to 1 1/4 because I wasn't sure that my supply volume would hold enough for a 1.5 inch. And so that's another part of the reason I did this. See, at 125 I'd be okay, but at 104 feet on a 1 1/4 inch pump, or 1 1/4 inch pipe, then I would actually be too long a run. And so that's where the standpipe comes in. So I'll just read the standpipe piece here to you next. Many hydraulic ram installations show a standpipe installed on the inlet pipe. The purpose of this pipe is to allow the water hammer shock wave to dissipate at a given point. Standpipes are only necessary if the inlet pipe will be longer than the recommended maximum length. For instance, if the inlet pipe were to be 150 feet in length in the above example, where the maximum inlet length should only be 104, or in my case with 1.5 inches, 125. The standpipe if needed, is generally placed in the line the same distance from the ram as the recommended maximum length indicated. And in my case, I chose to do it differently because of the terrain I'm in and just the logistics of the site that I'm working on. It was hard to find a good place where I could kind of conquer the terrain. There's a lot of mud and swamp and rough terrain around me there, so I chose what I chose. I ended up doing 35 feet, which I think is a little bit longer than the minimum length recommended for a 1.5 inch pump, but not much. If I had gone longer, I probably could have gotten a little bit better efficiency, but I may go back and change that at some point in the future and put steel pipe in, but steel pipe is extremely expensive, so for now we're running PVC. Now let's see. The standpipe must be vertical and extend vertically at least 1 foot higher than the elevation of the water source. And I would say at least 2 feet higher, or even a little more. It's amazing how much those levels can fluctuate under changing water load conditions, so to speak. No water should exit the pipe during operation, or even perhaps a few drops can cascade out over it at the cycle at most. Most recommendations suggest that the standpipe should be 3 sizes larger than the inlet pipe. The supply pipe between the standpipe and the water source should be 1 size larger than the inlet pipe. This is very, very important. So if you're running an 1.5-inch ram pump, you want a 2-inch supply line coming into your standpipe. If you use an 1.5-inch supply line, your ram pump is always going to be short of water. You have to remember, we're working with gravity here, and the amount of volume you can deliver to that pump matters tremendously, because that pump takes on even a little bit of air, it will disrupt the pump's operation, decrease its efficiency, and possibly even make it shut off on you. So you want to make sure your supply line is always 1 size larger than the drive pipe on the pump. So that's an important thing to note. So if you're making an 1.5-inch ram pump, you want 2-inch supply line to your standpipe if you have to put a standpipe in. If you're making a 3-inch ram pump, you want a 4-inch supply line. If you're making a 1/2-inch ram pump, you want a 3/4-inch supply line at least. I'd say probably just go to 1 inch. Just do it. It's not that much more expensive. But that's an important thing. You want to make sure you have plenty of water volume coming into the standpipe so the standpipe stays full of water. The standpipe not only dissipates the shock wave, but it also acts as a water buffer place. It makes sure that you don't deplete the amount of water that you need to keep the pump running smoothly. All right, let's see. And I'll read the rest of this piece to you. The reason behind this is simple. If the inlet pipe is too long, the water hammer shock wave will travel farther, slowing down the pump pulses of the ram. Also, in many instances, there may actually be interference in the operation of the pump due to the length of the travel of the shock wave. The standpipe simply allows an outlet to the atmosphere to allow the shock wave to go somewhere. Again, this is not necessary unless the pipe will have to be longer than the recommended maximum length. So that interference thing they're talking about, if the pipe is too long, as the ram pump starts to cycle its next cycle, there's still a shock wave coming back through, and it will actually interfere with the cycle, and basically the ram pump will cancel itself. So you want to avoid that at all costs, because obviously you're not going to move much water if the ram pump is canceling its own action. Another option, you can use any kind of tank. You could use a big water barrel, anything you want as a standpipe. It doesn't have to be a pipe. It could be a barrel. It could be a tank. You just have to make sure that it gets enough water coming in and that it's tall enough that you don't have water overflow and end up losing a lot of your water out of it. You want to be higher than the level of the water that the supply is coming from. And we'll get into how to use the water level, the line level here later in this video. Okay, so I've started some leveling work and engineering work to prep for the ram pump installation to get an idea of what the actual math numbers are going to be. It is 53 feet to this big maple at the end of the long log. And so we're talking about just about 60 feet to our mark tree, and we got an elevation drop there of 70 inches.
so we're just under 6 foot to there. So looking at that, I really want to have a minimum 6 foot, so I'm going to go ahead and string another line off this way a little further and see if I can't pick up a few more inches by going that way, and then I'll figure out whether or not that makes sense pipe wise and all. But right now we got this line is perfectly level from the water level on the pipe. It's tied right at water level on the pipe, and it runs across level. I used a line level. Sorry for the sway, I'm trying to balance here on the log too. Sorry for the line, excuse me. So I used a line level to level the line, so you could see, or so I could figure out what the elevation drop is. And like I said, it's 70 inches, and well, we're going to run some more line out and get a better idea of how much more drop we can get. I also did a recalc on flow, and looks like we're flowing about 15 gallons a minute today. Okie doke. Strung another section of line up. Carried the level straight out from the pipe to the tree that we were pinned to before. Now the new line runs out over here, downstream further, and tags out over there. It's well, I would say it's about 8 foot off the stream bed over here at the end of the line. But I'm looking at this spot here, which is about another 50 foot beyond that tree, so it'd be 100 from the pond. And where that tape is right now, from the level point on the line to the center of the stream bed, not the bank, the actual to the stream bed, is 83 inches. So we're just under 7 foot. So we get our 6 foot that way. And that's really awesome. That means we can produce plenty of pressure to get us up the hill and to the tank, or tanks. Yeah, so it looks like this is going to be the spot. We'll have to clear this all along the stream edges on either side to make working in here easy, and then we'll have to run a line out and deliver the water. Minimum drive pipe length for this pump design, I think, is 25 feet. It might be 35, so we'll probably come to that tree and then start our drive pipe from the tree over. So we'll just come to that tree at level and then do our drop from there on in. And that should do us for the ram pump. That's it for now.
Yeah, higher, it must be higher than the elevation of the source. Then attach inlet pipe to the tank. The tank will act as a dissipation chamber for the water hammer shockwave, just as a standpipe would. This option may not be viable if tank placement requires some sort of tower, but if the topography allows this, it may be a more attractive option. Yeah, and that's another thing to consider. Depending on where you're setting up, your standpipe may have to be pretty tall in order to compensate for the terrain you're working with. And I would not recommend putting a big barrel on top of a tower unless you have serious construction skills, because water is pretty heavy at 8.33 pounds to the gallon. You get a 60-gallon drum full of that, you're talking close to 500 pounds. You don't want to end up with that coming down on your head. So be sure that that's not going to happen to you, I guess is what I would say.
So this is my ram pump setup. Don't mind the pieces parts. Spring's coming. I got some pieces parts cleanup to do. So there's a spring over there in the reeds, which you can't see through the reeds at the moment, but rest assured there is a spring there, and that's the spring that feeds this pond. It puts out nice clean water. We've had it tested down at Bard at their lab, and regardless of the cleanliness of the water, you can still pump it, right? So
This pipe coming across from the spring is a 2-inch pipe. It runs through the dam and then down to the standpipe. The total distance of this pipe, this 2-inch supply line to this standpipe, is 117 feet. And so I'll pull up calculations here, or maybe I'll throw them up here on the screen as an overlay. If you look at the charts and do the calculations for a 1.5-inch ram pump, which is what I calculated there was enough water volume to support, you don't want to exceed, well, let's see, for a 1.5-inch ram pump with a 2-inch supply line, you don't want to exceed 100 feet to the ram pump, or 105 feet, something like that, or you'll end up with too much back shock going all the way up this line, and so you have to put a standpipe in to relieve that shock. So this pipe runs at 117 feet and hits the standpipe, and then there's another 35 feet that it goes from the standpipe to the ram pump. We'll get into those calculations too when we get back inside, and I can pull some nice numbers and charts and information up for you. So the first thing I did was come out here and measure water volume coming out. That was before any of this piping was here, so I had to use a fairly archaic method of measuring. So I measured the water volume. At the time, it was springtime, it was getting about 10 to 15 gallons a minute. I worked with springs before, so I knew the spring could be developed out a little bit more. But I figured 10 gallons a minute would supply an 1.5-inch ram pump right on the edge, and I knew I could scale the size of the pump down, and I wanted to move as much as water as I possibly could. So I started with 1.5 inch, knowing I could fall back to a 1-inch ram pump if I needed to. So in order to get water volume calculations, one of the easiest ways to do that, if you don't have a place, well, first of all, let me say, the easy way to do that is to take a 5-gallon bucket and hold it under your outlet and figure out how many seconds it takes to fill it, and then calculate, how many gallons a minute you're getting from that. Obviously, that's the easy way. Most cases, if you're developing a ram pump, you don't have a nice easy pipe already there to capture the water from. You may not have a pipe handy that you can divert the water, all the water in the stream from, or from the pond or your source, into a bucket. And if you don't have that, the next easy way to do that is to pick a spot in a stream like this, where you have a given depth and width, and then calculate the speed at which the water is traveling, and calculate using depth and width what the volume is, and then use the speed to calculate how fast that volume moves through. So we'll go over that in a minute, but basically in this case you can see it's I should have brought a measuring tape, but it's about 1 inch deep, and it's maybe about 10 inches wide or so where the water is actually flowing. And the real simple way to do this is to take a measuring tape, mark a length, drop something that floats on it, see how long it takes to travel that length, then you have how much volume is moving at what speed. We'll get into those calculations a little bit deeper later in this video, but I just wanted to illustrate the concept for you. Alright, then the other thing you need to know for a ram pump is what your total fall is. Now there's a couple ways to calculate that as well, but we'll go over the 2 easy ways. One, you can take something like a garden hose, get it into your water source up above, start a siphon on it. If you don't know how to start a siphon, we could go over that, or you can ask a question in the comment below. You start a siphon on it, you bring it down, and then wherever you bring that hose end up, this is called a water level, you'll reach a point where you hit equilibrium, where water stops flowing out the end of the hose, and where you drop the hose back down a little bit, it starts to flow. When you come up a little bit, it stops. That's your level point. And then you can use a measuring tape to take your tape drop and figure out what your fall is. In this case, we have about 6.5 feet of fall from the top of the pond to where the ram pump is. I used a combination of a water level line like I was talking about, and the other thing I used was a string level on a string
and I set a stake up at the water line, right at the water's edge, and I ran a string from that water's edge out level, and I ended up having to come to a post here and run another string, or extend that string level again out to where I wanted to set the pump. And then when I got out over the pump with a level string running level from the water level, you can just drop a measuring tape down and you figure out exactly what your drop is. So those are some key pieces that you're going to need to have to design and determine whether your site will support a ram pump and installing a ram pump. Once you have those, you got some calculations to do. And I think I've covered everything out in the field here that I want to cover. We'll get into calculations later in this video, but I just wanted to make sure that in daylight you could see what this site is, so you can better understand how to go about making these calculations. So what we'll do now is we'll go back inside and we'll make some calculations based on that. And we'll talk about all the little eccentricities and logistics and details that go with designing a ram pump and making it function like you want it to. Alright, so that's it for now. We'll go inside and we'll talk turkey.
Okay, so one of the core concepts you should understand right off the bat for building a ram pump is vertical foot and how it relates to pressure and head. So head is the distance of vertical drop, and it can be expressed in positive or negative values based on what you're doing. But in general, for every 1 foot of vertical rise, you get 0.433 pounds per square inch of pressure at the bottom of that water column. So as you go up 1 foot, 2 foot, now you're at 0.86. 3 foot, you're at 1.299, and at 4 foot you're at 1.732 pounds per square inch at the bottom of that water column. This will be an important part of building your ram pump because you're going to need two basic calculations. Number one, the vertical foot of head that you need, or that you have, from your water source to your ram pump, or where your ram pump will be placed. And the other one you need is the vertical foot of head that you want to pump to, because if that ratio isn't high enough, you won't be able to deliver a specified amount of water to the location that you want to, and the height that you're pumping to will affect how much volume of water you will actually deliver. So using the line level and the water level techniques, you can calculate, most likely, hopefully in your situation, from your water source to your ram pump. Okay, and so to calculate the elevation from your ram pump to your delivery point, you can use several different methods. I would not count on Google Earth. If you have a GPS unit, you could probably get reasonable accuracy, but know that that could be off as much as 30 feet on vertical elevation also, even with good satellite coverage. So the best way to do it is to run a line level and drop measurements, and you can do series of strings level and just keep adding the drop measurement across the strings. And another way to do this is you can use an orange marker and a scope with a level, and you get the level set and you shoot the far point. This is kind of like surveying or using a transit. If you have access to a transit, I highly recommend that. That is really a better way to do it. Or if you have access to an engineer who can do elevation datum, that's a possibility as well. Although typically that equipment is quite expensive to have someone come out and actually take elevation shots for. So I hope this helps you understand the basics of water pressure as it relates to elevation change, or vertical foot of head. One other means of calculating the vertical height going either to your ram pump or from your ram pump to your delivery point would be running any sort of pipe or hose down
from the highest point and filling that pipe or hose with water and putting a pressure gauge at the bottom, and you could measure the pressure and calculate very accurately what the vertical distance of fall is. So that line would have to be sealed completely, and you'd have to fill it with water from some source by whatever means necessary. But that would be an accurate way to get exact vertical elevation over long distances and multiple swales, or where there's trees in the way obstructing your view. That would be another way to do it. However, if you're going to do that, you might consider doing it in the delivery line size that you want to select for your ram pump, and then after you use that for your pressure calculations and your elevation calculations, if you decide you can and want to go ahead and build a ram pump, you'll already have the delivery line for the system. These are just some other thoughts on how you can arrive at accurate elevation datum for designing and building your ram pump. Okay, let's briefly go back to the measuring the trench method for volume calculation. Real quick, we'll look at this box. Basically, that's what we're simulating in the previously mentioned trench method. You want a depth, you want a width, you want to make it relatively uniform, and you can even take a few boards and set in the stream bed and channel the water through them so you get a nice uniform height. The more accurate you can represent that, and the more accurately you can measure the speed, the more accurate your actual water volume calculations will be. But for example, let's look at this box and consider it to be as though it were the stream bed, or a box set into the stream bed with water flowing through it. So 3.5 inches by 2.5 inches by 9 inches. Let's calculate that volume. So 3.5 inches by 2.5 inches by 9 inches is 78.75 cubic inches. There's 231 cubic inches in a gallon. We'll call it 79 for easy calculations. And I did that backwards, so it's we'll say 79 over 231 cubic inches in a gallon. So that box is 0.34199 gallons, roughly. So about 0.35 gallons for every time that the water cycles through that box. So let's just consider that a second. So if the box is full of water, I'll demonstrate. And said water is flowing at a given speed, now we can calculate how many times per minute, effectively, this box is replaced in water volume. So in our calculation, we're looking at a water depth of 2.5 inches, a channel width of 3.5 inches, and we're taking a 9-inch segment of that and measuring the speed the water travels through it. So if it takes 60 seconds for that water to travel that length, then you're looking at 0.35 gallons a minute. And then of course you can calculate from there and figure out speed. Say it takes 10 seconds to traverse that, then you're doing 6 times 0.35, because there's 6 10-second segments in a minute. And let's see, 6 times 3, 18. So you're looking around 20 gallons a minute. So this is just an example of how to do this. But remember to picture this full, like this shot here. So just remember, every time this fills up, that's 0.35 gallons. And then you can make your calculations easily based on the trench, the water depth, and the speed at which it's traveling. Okay, so let's just hash this out quick. If it is, we'll say 0.35 gallons, and if it takes 1 second for that to traverse your float down that channel, and that's 0.35 gallons, that means in a minute you've moved 21 gallons. So then from there you can basically say quite easily how much actual volume you're moving. All you got to do is take a measurement in seconds and crunch those numbers like that. I'll throw a formula up quick, and then you have your volume flow. And of course, depending on your water source, you should adjust this for the time of year. If you have dry seasons, your water flow will likely reduce. So try to design a ram pump system that will work at the minimum water flow for the season, so you have guaranteed water delivery throughout the season. I have another video on ram pump scalability. You can actually take a larger ram pump design and scale it down with a smaller impetus valve. So that is also an option, and I discovered that after building the 1.5 inch during dry seasons, and I was able to scale down to even as small as a 1 inch valve. Delivers a lot less water, but sometimes some water is better than none.
Okie doke. Well, now we're going to get into the meat of it. First, we'll start with just going through the operation description as they describe it, because they do a very good job of describing it. So let's start with that. Operation. The pump will require some back pressure to begin working. A back pressure of 10 psi or more should be sufficient. If this is not provided by elevation-induced back pressure from pumping the water uphill to the delivery point, water trough, barrel, etc., use the 3/4 valve, part 7, to throttle the flow somewhat to provide this back pressure. So basically you're closing the output valve to create back pressure so the pump will run. It won't run under 0 back pressure. You need to have some resistance. Otherwise there's not enough pressure to keep it functional. As an alternative to throttling valve part 7, you may consider running the outlet pipe into the air in a loop and then back down to the trough to provide necessary back pressure. A total of 23 feet of vertical elevation above the pump outlet should be sufficient. Notice how that corresponds if you divide 23 over 0.433 pounds per square inch. That gives you that 10 psi they're talking about. So we covered that before, just wanted to reference it so you understand where the 23 feet is coming from. This may not be practical in all cases, but adding 8 feet of pipe after piping up a hill of 15 feet in elevation should not be a major problem. This will allow you to open valve number 7 completely, preventing the stoppage of flow by trash or sediment blocking the partially closed valve. It is a good idea to include a T at the outlet of the pump with a ball valve to allow periodic flushing of the sediment just in case. And you'll notice if you go back and look at the video on my pump, you'll see I have a T in there and you can flush right out directly, and I highly recommend that. That's super effective for flushing, and also if you end up wanting to pump water somewhere else, you can just plug a garden hose in or whatever your fitting is and move water elsewhere. You can use it for washing stuff up when you're working on the pump or whatever. Very handy to have a secondary outlet. Anyway, initially the pump will have to be manually started several times to remove all the air. Start the pump by opening the valve 1 and leaving valve 7 closed. We'll just go back to this diagram quick so you know what I'm talking about here. Valve 1, this is the output valve. I'm sorry, that's the inlet valve, and valve 7 is the outlet valve. So valve 1, valve 7, pressure chamber, pressure gauge, delivery line, drive pipe coming in on this side. Let's see, the pump will start with valve 7 closed completely, pumping up to some maximum pressure. Start the pump by opening the valve 1 and leaving valve 7 closed. Then, when the swing check number 4 shuts, manually push it open again. You'll have to do this several times till it builds up enough pressure to operate on its own. The pump will start with valve 7 closed completely, pumping up to some maximum pressure before stopping operation. After the pump begins operation, slowly open valve 7, but do not allow the discharge pressure, read the pressure on the gauge, to drop below 10 psi. If you don't have a gauge, just very gently crack that valve open. I use the ball gate valves because they're a nice simple valve, but you might be better off as far as that goes for regulation using the older screw type valve where it's multiple turns. So you might consider that in your design. I may have to push valve number 4 open repeatedly to restart the pump the first few minutes. 10 to 20 times is not abnormal. Depending on your situation, I would say you could go up to 50 times. If you've seen my recent videos, the pump starts up, I think it's like 5 or 6. But this pump, my pump, is really tuned in now. I've really gotten it dialed in. Anyway, air in the system will stop operation until it is purged. They're specifically talking about air in the drive pipe, as we were talking about. You have to eliminate all air in the drive pipe. So before you even start this process, you want to make sure that your standpipe or your water source and your drive pipe are completely full and all the bubbles have bubbled back out through the top. So it may take, 20 or 30 seconds for all those bubbles to work their way out before you start up. The unions, gate or ball valves, and pressure gauge assembly are not absolutely required to make the pump run, but they sure do help in installing, removing, and starting the pump, as well as regulating the flow. And I'll add to that, another thing that the pressure gauge is very useful for is if you end up with a leak in your delivery line later on, especially if you're pumping to pretty high elevations, like mine, for example, pumps 72 vertical feet and about 900 feet distant. You can use that pressure gauge to figure out where your leak is roughly in the line by looking at the pressure gauge and doing the elevation calculation, and you know the approximate area to look on the line. I've got a video on that too. Maybe I'll throw a link down below if I can remember when I'm done crunching all this. Alright, pump performance. Some information suggests that typical ram pumps discharge approximately 7 gallons of water through the waste valve for every gallon pressurized and pumped. The percentage of the drive water delivered actually varies based on the ram construction, vertical fall to the pump, and elevation to the water outlet. The percentage of the drive water delivered varies from approximately 22% when the vertical fall to the pump is half or 50% of the elevation to the water outlet, down to 2% when the vertical fall is 0.04 or 4% of the elevation to the water outlet. Rife Hydraulic Engine Manufacturing Company offers the following equation, and I would say this equation is very effective. It's 0.6 times Q times F over E equals D. And we'll go ahead and break that out. Q is the available drive flow in gallons per minute. F is the fall in feet from the water source to the ram. E is the elevation from the ram to the water outlet. And D is the flow rate of the delivery water in gallons per minute. 0.6 is an efficiency factor and will differ somewhat between various ram pumps. For instance, if 12 gallons per minute is available to operate a ram pump, then the pump is placed 6 feet below the water source. The water will be pumped up an elevation of 20 feet. The amount of water that may be pumped with an appropriately sized ram pump is 0.6 times 12 gallons a minute times 6 foot over 20 foot equals 2.16. So 0.6 is the efficiency, 12 gallons a minute is delivery into the drive pipe, 6 foot is the fall from the water source to the ram, and 20 foot is the vertical head from the ram pump to the delivery point. Please pay special attention to this. This is not the distance from the water source to the delivery. This is the distance from the ram pump to the delivery in vertical head. And so that equates out at 2.16 gallons a minute. The same pump with the same drive flow will provide less flow if the water is to be pumped to a higher elevation. For instance, using the data in the previous example, but increasing the elevation lift to 40 feet, 0.6 times 12 gallons a minute times 6 foot of fall over 40 foot of delivery point works out to about 1.08 gallons a minute. So you notice if you double the delivery height, you about half the water volume. It's almost exactly half according to the formula. Obviously in real time it may fluctuate a little bit. Anyway, that brings us down to this table here, table 2. This is gold. This is gold. This gives you the general parameters, and this is one of the charts that was super useful for me on, what size ram pump am I going to design based on the water flow I have and what can I expect to deliver up top. Now, I mentioned previously that I used Google Earth and GPS and actual measurements in the field. I initially took GPS data for my delivery elevation from Google Earth. I knew it wasn't super accurate, but I didn't think it would be quite as far off as it turned out to be. According to Google Earth, elevation from my ram pump to the delivery point would be about 42 feet. And in real time, after I started pumping, I found out it's 72 feet. So I was expecting about 1.5 gallons a minute, I think. Yeah. So I was expecting somewhere around 1.5 gallons a minute based on this chart here. If you look at the drive pipe at 1.5 inches, 3/4 inch output for delivery pipe, and I expected a pump inflow of around 12 to 15 gallons a minute, and I figured around about 1.5 gallons a minute delivery, but that was based on a 42-foot elevation, and since it turned out to be a 72-foot elevation, I get about 0.85 gallons a minute when efficiency is really right on the money and flow input is good. Still, at 0.85 gallons a minute, and if you can run every day for 1,440 minutes a day, I'm still taking home 1,224 gallons a day, which is absolutely way more than I need for my homestead and farm here. So that is a good chart to go by. Let's just look at table 3. They're talking about 1.25 inches, schedule 40 PVC pipe. Oh, I should mention that as well. Don't use cheap PVC for your drive pipe or for your pump parts. Use at least schedule 40. Even better if you can afford schedule 80, although that is significantly more expensive. Use at least schedule 40 PVC if you're going to use PVC for this. Again, we want super rigid pipe. We want pipe that doesn't flex, because the more the pipe flexes under that pressure, the less of that energy is transferred through the secondary valve and used to pump water. You end up losing that energy in flex of the pipe. It's either outletting at 3/4 inch, schedule 40 PVC. I will say this, if you're trying to save some money and you want a line that you can run all over the place and not have to do a bunch of PVC glued fittings and all that sort of stuff, I would use the black coil pipe, or poly pipe it's called, or well pipe. It's well, you'll see it in my videos there. It's the black stuff, and it's super flexible. You can get fittings for it cheap. You can cut it and put new fittings in it real easy, and you don't have to use PVC glue. I would recommend you get the barbed type fittings and use appropriate stainless steel clamps for it if you're working under any serious pressure. They're talking about different pressure chamber sizes. See, they're saying 36 inches here for the 1.25 inch pump. I would say that's a good size to go with anything 1.25 inch, 1.5 inch. I would say that probably even would work for the 2-inch pump. You might want to go to a 48-inch length chamber for that. And they're using 4-inch here, and I have 4-inch on mine as well. Let's see, they're doing inlet pipe length 100 feet, outlet 40, drive water elevation 4 foot. So they're driving with 4 foot there. And this is some real world tests that they did. We'll go over this. I did discuss this briefly earlier in the video about the threaded plug, but this will give you a good understanding of what happens when if your bladder bursts in your pump, or if, like me, you're not running a bladder and you're just using the air pressure in the chamber. Over time, that air will dissolve into the water and you'll lose that air ballast in there. So it's good to shut the pump supply water off occasionally and open that secondary T valve. This is another reason that's really handy. And drain that out and let air flow back up into that pressure chamber. And then when you close that back up, you have trapped air again. If you don't have air in there, this pump will tear itself apart because all that water shock is not being cushioned by anything. That water shock ends up transmitting throughout the entire system, and it will tear fittings apart. You'd be amazed how much actual energy is there. So let's just look at this quick. We'll read the note first. Note that we used a 4-inch threaded plug and a 4-inch female adapter for our test pump instead of the recommended 4-inch glue cap shown in the figure. 2 days after installation, the pump air chamber was effectively waterlogged due to leakage past the threads of these two fittings, which was shown by the pronounced impulse pumping at the outlet discharge point. If the pump were allowed to remain waterlogged, it would shortly cease to operate and may introduce damage to the pipe and other components due to pronounced water hammer pressure surges. The large range of expected values for shutoff head is due to the unknown efficiency of the pump. Typical efficiencies for ram pumps range from 3 to 10 feet of lift for every 1 foot of elevation drop from the water inlet to the pump. And so I said generally 1 to 10, but you can see here that depending on what your water delivery needs are and your situation, you can actually move water a lot further than you might expect. Anyway, if you look at this at installation, their shutoff head was 5 to 17 psi, 22 psi here. After installation of the water log, it was 50. After clearing, it went back to 22. Operating head at 10 psi, 10 psi, 10 psi. Flow rate 0.5 to 1 gallons a minute. They had 0.28 gallons a minute in installation. After installation, when it was waterlogged, they were getting 1.5 gallons a minute, but surging. And then after they cleared the waterlog, it went back to 0.33 gallons a minute. So that's one thing you'll notice if your bladder starts to go, or if your air space in your pressure chamber starts to fail. You'll see on the delivery side, you'll see each pump pulse cycle come out in the form of a surge of water, and it'll start surging. So if you see your water delivery surging on and off in pulses instead of a fairly steady flow, that's an indicator you got a pressure chamber problem, and you should probably get down there and shut it off as quickly as possible to avoid damaging your pump. Let's see, they got a couple of snapshots here. We'll just let you have a look at these quick. This is a good diagram, general diagram of how it works. And you can see we're taking this little bit of fall here through the ram pump, and we're pumping to this very high height to the water tank. And they illustrate head here as well. Oh yeah, and they're showing one without a standpipe here, and then here you're seeing one with a standpipe, or a water tank they're calling it, but it's basically a standpipe. One point I want to make about that, I said you wanted to make sure that your standpipe was up above your water source level. I mean the top of your standpipe. The bottom of your standpipe should definitely be well below your water level. What you're looking to do is set the standpipe about midway in and out of the level of your water source so that you have a constant volume supply. I hope I've made that clear. This installation is one option used where the inlet pipe is longer than the maximum length allowed. The open water tank is required to allow dissipation of the water hammer shock wave. I think we discussed that previous, but I just want to make sure you get all the details here. Here's another sample installation. This is another option used where the inlet pipe is longer than the maximum length allowed. Remember, we did our calculations early on for different pump sizes. The standpipe, open to atmosphere at the top, is required to allow dissipation of the water hammer. You can see they're using an actual pipe in this example, and in this example they're using a tank. It really doesn't matter what you're using for hardware. What matters is that your water levels and your volume supplies are good. And I want to remind you once again that whatever size drive line you're using for your ram pump, you need to be one pipe size bigger than that for your supply line. Remember, we're working with gravity feed here. So if your ram pump drive pipe is 1 inch, you want inch and a half pipe feeding your standpipe. If you're an 1.5 inch ram pump drive pipe, then you want 2 inch feeding your standpipe. At least you can go bigger than that if you want, and so on and so forth. Let's see, I think I think that's about everything. They're just kind of illustrating some different pieces here. Anyway, again, I'll show the link to this down in the bottom, and you can go check it out yourself. That formula for calculation I will put up as well. This is very important for figuring out whether you'll get enough water out of your situation or whether it's worth building the ram pump. But you do need to take those measurements and calculations as I previously discussed, and like I said, the more accurate you can do that, the better off you're going to be in determining what your actual real-time volume production can or will be.
So here we are back out in the field at the spring head. Few more details to go over here in the field from a practical perspective. Just wanted to finish up on these details. So one, you want an intake suction strainer for your source water so you don't get debris in your pump. Debris can damage your pump. It can also get into that secondary spring check valve, and it will actually lock the valve open if you get like a stick wedged in there. I've had that happen, and then your pump stops working and you don't know what's going on until you take it all back apart. So before you run any water through your piping, make sure you have a good filter on. This filter actually is clearly due for replacement again. I put this in just a couple of years ago. This was an old like air scrubber type filter, and I just took all the carbon filtration stuff out of it and used the caging. That worked pretty well. You want a relatively large size filter so you don't have one little spot sucking all kinds of gunk on the filter and clogging it quickly. So I would say look for something that's of large size, and screen mesh at least as small as that as your final mesh. You don't want to let anything bigger than that in. I would say that's probably 1/8 inch. That's probably a decent size for an 1.5 inch ram. If your ram pump is smaller, you have to make your screen smaller, but you'll also be pulling less water volume. So that's just all to be kept in mind. There's various different methods for making intake filters. If you request a video on that, I may do something like that. For now, let's move on down to fittings. So here we are back down at the ram pump site. Just want to point out a couple of things. For my setup to pull, I wanted to pull fresh spring water to the ram pump and not just pond water. So you can see I've isolated the spring up there, and I'm pulling the spring water straight through the pond without touching the pond water. It gives a nice clean spring water feed, and we've actually had it tested and it's drinkable, so that's very nice, and it's excellent spring water. Anyway, all that aside, two things here. We have a valve here, which I broke the handle part of the valve, so I just use a pair of channel locks to turn this valve. But this valve makes it so we can shut water off to the standpipe and work on this system, everything below the pond dam here. One of the reasons I want to mention, one of the reasons that I put a standpipe in here is not only because of pipe length, but also because of the shock wave that's generated. If you dissipate that at the standpipe, then you don't have as much shock wave coming back up your supply pipe, and anytime you're running through a dam, you don't want to be putting shock on it, because you'll create a leak around the pipe, and then it will erode the dam, and then you won't have a dam. So just an important point to note: if you're going to be piping through a dam, make sure you put a standpipe in to dissipate that shock before you go back through the dam with your piping network. Alright, another thing that we use here, these are super useful. They're expensive, and I recommend you get the Schedule 80. These are really nice. These are called unions, and they basically just thread together. You can get threaded and you can get slip fit. I recommend you get the threaded fit and get the threaded end coupling for the pipe and glue that on. And then if you have a problem later on, you have to replace pipe, you can unthread these expensive fittings from your broken pipe if it breaks right up to it on you, and you can save the fitting. Otherwise, if you use the glue fittings, if the pipe cracks up to the fitting, you lose that. And those are about 20 or 25 bucks a pop, depending on the size you're working in. At least 1.5 inches, 2 inch in that range. So that's something to consider.
Let's go down and look at some other pieces, parts. So the dam is right about here. We've just come down our supply line, which is 2-inch pipe coming into our standpipe. This is a great place for me to show you a unit. Sorry I had to do this at night. Wanted to finish this video up. So basically there's just two plastic ends. The other side of that, see if I can do this without going in deep in the mud. Yeah. The other side of this is supposed to have a rubber gasket. I gotta pick up another one. But under low pressure like this, it's not a big issue. Anyway, these two pieces fit together. And then you can see this is threaded. And this collar is threaded on the inside. And it just threads together. And then that way you have an easy way to take your pipe for working on it. Or I don't know if you saw in the beginning when I first started flushing here, all the mud that came out. It's a good way to flush all the mud out. We let the pump shut off at the moment, so we'll kind of sequence our way up through this. Alright, on to the next part. One sec. We'll just work our way through the rest of the standpipe here quick. So we've got a low input coming in. You'll notice I use 4-inch PVC pipe T with a 2-inch output on the T, so I can pipe my 2-inch into the 4-inch standpipe. The bottom is a 90-degree 4-inch, and it's got a 4-inch threaded end cap on it. So basically the standpipe also acts as a sediment and small rock trap in case something does get through the screen. It falls out in here or floats out to the top instead of going into the pump. So when you stop the pump and dump the flush open, you can flush it out. The other thing that's really handy to have is another output on your standpipe. Pardon my footing. And I have a 2-inch here. This is a nice way to be able to just shut water off to the pump without having to shut that master valve off. And also another way to flush through the pipe if you just want to open it up to flush. Let's see, other factors. We are about 3 feet below actual water line, so water comes up to about here. So you can see that in scale. Anyway, I would say you're coming out of your standpipe, you're going to want to set your drive pipe output to your ram pump lower than you think it is. So I would say go significantly below water level, but keep in mind that you do want to keep a relatively steady slope going out to the pump itself. So those are factors to consider. Try to stay lower, because when your water supply goes low, and this pipe won't fill up as much, and you want to make sure that you're still below where you pick up air bubbles, at least until you run out enough water supply to run the pump. So the standpipe is filling now with water. The ram pump is off and the valve is open at the moment. So what we'll do is we'll go through the startup sequence here quick. Real quickly I'll point out this whole bottom part of the standpipe is glued together. The top I did not glue on for a couple reasons. One, so you can take it off to work on it. And two, if you add a float gauge later like I did with a couple of bottles and a reflector post, now you have a way to know where your water level is at a glance on your standpipe. It also makes it so if something gets stuck in there, you can get at it to get it out. Lots of handy things about that. I'll just step back quick and let you see the gauge is low at the moment because the pump is open, it's just draining off water. We'll shut it off and you'll watch that gauge climb up in a sec. Okay, here we are. And I just want to point out that I used a, that's a little loose. I used a foot valve instead of a swing check valve. I highly recommend the foot valve because it's a guided valve, and you can add weights if you want to change the stroke cycle of the pump. You can tweak your pump efficiency, water volume delivery, and you can scale it back if you need to for low water supply to some degree. Other thing that I do, I take two PVC fittings, 2-inch on the 1.5-inch brass pump that I have, and I slap them over, and that way we don't end up with wow,
Somebody's wearing some perfume. Wow. Anyway, that way we don't end up with the water spitting off both sides on us. So I shut that off, and you could hear the bubbles gurgling up, I'm sure. And now you can see, if I zoom in on the standpipe, that reflector is sitting up out of there now, indicating the reservoir is filling up. So we'll see if this will start up. It's been open for a while, so it hasn't had a chance to accumulate a lot of water in the spring, but we've had good water this year, so hopefully it'll go. So let's see. I'm going to close both the valves for startup, and that pressure you're hearing is pressure sitting on the valve from when the pump was running before, probably. So let's just, alright, we've dumped off all the pressure. And see, this pump starts right up pretty easy. But it's well tuned. So there you go. We'll open the output valve. You can see all that pressure coming off from that. That's because the delivery line is frozen right now. It's one of the points it crosses under the soil. But that's it. That's all there is to it. I would use brass valves for your spring check valve, and or stainless, even better if you can afford it. I would put a union here, right on your input to your pump as well, and I would put a shut-off valve right in front of that probably. I haven't done that yet, but as you saw, I can bypass. Let's see. The rest of this should be steel. These other fittings in between should be steel. And I would do PVC, you know, different union sizes to make your fit up to get to your pipe size. I don't have 4-inch here. I have 3-inch actually. And it's maybe 36, 42 inches tall, somewhere in there for the 1.5-inch pump. And that's plenty of space. Probably could do half that and be okay. Okay, I think that's the majority of it. I did mention having the extra T valve. That's this right here, so you can dump off if you need to dump off. And I also have a shut off on the output, so I can shut off the output and do testing or divert water. One last important detail, mounting. You should really follow their advisement in the manual and like pour a concrete base and set bolts in that and be able to strap your pipe to it with bolts and nuts. If you can't do that, you can do something like I did here. I got a big piece of railroad tie, and I kind of set the pump up on that, and then I drilled holes through that, and I drove 5-inch rebar in, not 5-inch rebar, I'm sorry, 5-foot rebar in, 1/2-inch rebar down through those holes to anchor this. And even given that, I could probably improve my efficiency a little more if I set some concrete in here and really shored this up solid. You want to anchor your pump really well. There's a lot of force there. Think about it, a 40-foot long pipe, 1.5 inches in diameter, moving water, slamming on one spot. Okay, that's it. Okay, I think I'm finally done with this video. We've covered a lot of stuff here. Thank you for bearing with me if you've made it all the way to the end of this video. It's going to end up somewhere around 1.5 hours all said and done by the look of it. Appreciate you watching it. If you have any questions or comments, please do so down below. Don't forget to like and subscribe. Please share this video with friends if you know other people that might be interested, even just in checking it out. Your views really help my channel, and it helps me keep making videos like this. So thanks to my viewers and subscribers. Thanks for watching, and I hope we'll catch you in future videos.